Welcome back, guys. Last week, we were discussing the topic of manipulating equations with arbitrary variables. And you'll remember that one specific type of equation that we looked at the start of the week at was, or were, the following exponential equations, where you had, say, x squared is equal to something, or conversely, the square root of x is equal to something else. And what we learned at the beginning of this particular chapter was that one way that you could, say, solve this particular problem would be to take the square root of both sides. And if you had taken the square root of both sides, you would get x is equal to plus and minus 3, where there are two possible solutions for what your unknown number happens to be. However, while it's true that you can take the square root of both sides, consider what would happen if you had the following polynomial. Suppose you have the polynomial x squared plus 6x plus 9 is equal to 0. Now you're in kind of some trouble, right? Because even if you use, say, adding a negative 9 to both sides in order to isolate your x terms, you've got x squared plus 6x is equal to 0 plus the negative 9 will be negative 9. Now you've got this expression where we haven't really done much in the way of actually helping ourselves find an answer because, if we were to, say, use algorithmic methods in order to determine what the solution of x happens to be here. And in this instance, how that would work is you would have to guess at a specific x value such that the entire equation on the left-hand side equals 0. For this particular problem, when you've done some rearrangement, you're still left with trying to guess at some sort of an x value, such that now instead of x equaling 0, you have this expression, and we need to guess an x such that we get a negative 9. And it's not exactly much easier to do. You could say guess negative 2, and you check, is this equal to negative 9? And negative 2 times 6, that gives you, say, negative 12. And then negative 2 squared, that gives you a 4. 4 minus 12, does this equal negative 9? Well, we're indeed pretty close here. We get negative 8, but unfortunately, negative 8 does not give us negative 9. So then we might say, guess, perhaps negative 3 would be a solution. So you ask yourself, negative 3 quantity squared, and then 6 times negative 3, does this equal negative 9? And negative 3 quantity squared, well, negative 3 squared is the same thing as negative 3 times a negative 3. Negative negative is a positive. 3 times 3 gives you 9. So you have a positive 9 here. And positive and negative is a negative. 6 times 3 gives you 18. And in this instance, you would be able to obtain negative 9 is equal to negative 9. And so your conclusion would be, just using algorithmic methods, that your answer to this question, what value satisfies the equation of x squared plus 6x plus 9 equals 0? Well, the only value that satisfies that particular equation, or at least one of the values that satisfies this equation more precisely, would be x is equal to negative 3. And of course, we're stuck with the question of, is there possibly another solution? Just like here, where you had taken the square root of both sides and you were left with two possible solutions, the question would be whether or not there would be two possible solutions for this x is equal to negative 3. Negative 3 certainly satisfies this equation, but it's possible that there are other values that also satisfy this much more complicated equation. So what we're going to be talking about today is we're going to be talking about the subject of what are known as polynomial equations. Now, the first thing to note about polynomial equations is that depending on the equation itself, typically the polynomials will become much easier to solve or much more difficult to solve. In fact, we've already seen polynomial equations which we were solving for the past 3 weeks. We didn't call them polynomials, but we called them linear equations of one variable. So the most basic type of polynomial equation that you'd find would be, say, x is equal to some value, 7. And you'd say that this is an instance where you're dealing with a monomial. X is equal to 7. There's just one term here in your equation, hence the reason why we call it a monomial. Mono being Latin for 1. And IAL is a suffix which means number or name. It's kind of like noma in Spanish. So nom, it really means one number or one name. And so we would classify this particular single term as a monomial expression. Now, naturally, monomials come in many different types, many different categories. You could have a monomial x squared is equal to something, or a monomial x cubed is equal to something, or a monomial x to the fourth is equal to some value. So when we classify monomials, we're not necessarily saying anything about what is known as the degree of an expression or the number of the largest exponent. Rather, when I start classifying polynomials as, say, a monomial, what we're really talking about is how many terms exist in a particular equation or on certain sides of a particular equation. So you would say if you have one term, you're dealing with a monomial, and if you instead have, say, 2 terms or 3 terms or 4 terms, we would start to classify those as totally different entities. So, all right. Let's just kind of create a little bit of a table. And so the easiest polynomials that we work with, we call them monomials. Some examples of monomials would be just an x squared, x to the third, x to the fourth, 5x, 20x squared, 50x to the third, 102x to the fourth. These are all monomials. And one of the interesting aspects of monomials is it doesn't matter whether there's a number that is out in front, what we call a coefficient, of the polynomial. Okay, and it doesn't matter what the degree happens to be. The degree and the coefficients are their own properties of the polynomial, and they are important, but they're just not important in terms of classifying the difficulty of doing rearrangement or manipulating that particular polynomial expression. So the most basic thing that you could be given is just some formula that has a single term on one side of an equal side, and then you perform some sort of presumably 1 or 2 steps worth of operations in order to obtain your answer, right? But then you might have a step up from that. You might have, say, what are known as binomials. Binomials are more complicated expressions. Bi means 2. Again, nom means name or number. So 2 numbers. X plus 7. This is an example of a binomial expression. X squared plus x. This is also a binomial. 3x cubed plus 4x squared. These are all binomial expressions. And so here again, when we're talking about classifying the difficulty of, say, manipulating certain expressions, while the binomial is not necessarily as straightforward as, say, a monomial, generally speaking, a binomial would be the next easiest type of polynomial expression they could be manipulating, and as a consequence, it'll use the next easiest set of problem-solving strategies in order to manipulate that particular expression in order to obtain, say, an answer. So just two names, two numbers. Whenever you have two terms, and those terms could have, say, coefficients in front of them, the numbers themselves do not actually count as say, an additional term just because you have a 3 and x cubed here and a 4 and an x squared. Yes, technically speaking, there are 4 different numeric quantities that exist in this expression, but we would say that the 3x cubed is its own term. This is its own term, and the 4x squared also exists as its own term. And as a consequence, because there are only 2 terms, separated or punctuated by this addition symbol, you would classify this polynomial expression as a binomial. And then last but not least, you have what are known as trinomials. Trinomial expressions are more complicated than binomials, and there are a wide range of manners to solve trinomial expressions if there is in fact a solution. But trinomial expression will generally take the form of an ax squared plus bx plus c, where a, b, and c are constants. You may have something like an x squared plus bx plus c whenever there is not a number in front of your x squared term. But naturally, we classify trinomial, or these polynomials with 3 terms, 3 numbers, not by the degree of the polynomial itself, but rather the number of terms. So you could theoretically have, say, something pretty nasty like 15x to the 5th plus 6x squared minus 4, and this would also be a trinomial on a technical level. Okay, now let's talk about what are not polynomial expressions. Okay, not polynomial expressions would be things like exponential functions, logarithms, natural logarithms, as well as the trigonometric functions. Okay, each 3 of these would be an example of something that is not a polynomial. And as a consequence, if we ever came across this, we would say that this is not a polynomial. None of the uh, techniques that we develop for polynomial expressions would necessarily apply for these particular types of equations, or for equations that contain these operators. But another example of something that would be not a polynomial would be anytime you've got some term that exists inside of the denominator of a fraction, or for less obvious reasons, uh, anytime you've got, say, an x term or a variable that may be raised to the power of a negative exponent. So anytime you have what are known as negative exponents, or anytime you have, say, variable terms that are in the denominator, what you're dealing with here is you're dealing with what are known as rational expressions, but they're a little bit different than polynomial equations. Okay. So polynomial expressions or polynomial equations may be classified as monomial, binomial, and trinomial. And the degree of the polynomial is defined as the highest exponent of a polynomial expression. So when you've got something like 15x to the fifth plus 6x squared minus 4, you would say that the degree of this polynomial is 5, because the highest exponent of the polynomial itself is this x raised to the fifth power. So you'd say this is a polynomial of degree 5. You would then also say that this is naturally a trinomial, since it has 3 terms that are associated with it. And we said that coefficients, these are just numbers that exist in front of each variable term within an expression. Okay, so coefficients and degree of polynomial, they're interesting. They're definitely going to influence the types of manipulations that we can perform on a given polynomial, or the manner in which we can perform those specific operations. And what should be noted before we get to exactly how one might solve x squared plus 6x plus 9 is are the specific rules that we need to develop regarding how polynomials, say, add with other expressions, etc. And we've actually kind of discussed this topic a little bit already in class earlier in the semester, and we called that addition of like terms. But we're now going to revisit this concept of addition and subtraction of like terms within the context of, say, more complicated polynomial expressions. So when I say addition and subtraction of like terms, you might have a polynomial expression 5a squared b added with 10a squared b. And the only thing that really is important when it comes to addition or subtraction of polynomials is whether or not the variables and the degree are exactly the same. So you've got an a squared and a b. The b is raised to the first power. The a squared is raised to the second power. So you would say that in this instance, these are like terms. And as a consequence, we can go ahead and add 5 plus 10 together, and we get 15. A squared b. But note, very critically, 5a b squared plus 10a squared b. These do not add together because the specific degree of the polynomials happens to be different. In the first polynomial expression, you have a b squared term. But in the second polynomial expression, you have an a squared term. And so what's happening here is that you've got a 5 times a times b, because that's what b squared literally refers to. So there's my b squared. And then I've got a 10a squared b, where the a squared is the same thing as a times a. So I could have rewritten this a squared as 10 times a times b. Okay? And so the specific arrangement of, say, variable terms, because I've got an a squared and for my term on the right, and whereas I have a b squared for my term on the left, we would say that you would not be able to add like terms, because what's going to happen is when we add like terms, we're always using or exploiting what is known as the distribution law. And so how the distribution law works is that you essentially can locate terms that are in common inside of an expression. And in this instance, you have an a and b in common. So you might write a times b outside of a sequence of parentheses. But the terms that you don't have in common, in this instance, the 5b, and the 10a, you would have to write as being the terms inside of the parentheses that are remaining. And what's interesting here is that you can clearly see that the B term and the A term, well, it's like adding 5 bananas with 10 apples. These are not like terms. The process of going from a complicated polynomial expression to something where you've got, say, um, almost a distribution law style setup is what we know as factorization. And as it turns out, factorization is going to be one of these critical techniques that we're going to talk about over the next coming weeks. So we can add like terms. What are the implications of this? Well, if you have something like 5a squared b plus 10a squared b minus 13a squared b plus 14a squared b. And then what's going to happen is the following. First of all, you may add your like terms outside of the parentheses together. You have 5a squared b and a 10a squared b. That gives you 15a squared b. And of course, we're subtracting from this the quantities that are inside of the parentheses, which in this instance are also like terms. So by PEMDAS, if you look inside of the parentheses, we see 13 and 14 added together because they're like terms. We get 27 a squared b. So 15 minus 27, what does that give us? Well, let's take the difference of 15 and 27. 7 minus 5 gives you 2. 2 minus 1 gives you 12. So we get 12 a squared b, and this, in fact, will be a negative 12a squared b because 27 is a bigger number than 15, so if I'm taking 27 away from 15, I will get a negative. So that'll be your answer. What's less obvious to students is that as we're adding and or subtracting like terms, we have to be aware of the importance of the commutative law as well as just the definition of negative numbers. So when you have a negative number, recall that that's the same thing as -1 times a given number. That is a critical fact to remember. But then also remember that whenever you have a minus some value, that's the same thing as a plus a negative something, which we may, in some instances, simply want to write as a plus -1 times that something. These two just basic definitions you need to hold on to. So put a star in your notes and just remember, I might need to invoke either one of these terms at some point in the future. But for now, we'll move on. Suppose we've got a little bit of an easier problem statement. Perhaps we've got 5x squared plus 10x plus 25. And from this, we're subtracting 8x squared plus 2x plus 7. All right, what is this equal to? Now, in this instance, by easier, I guess I meant you've got a polynomial expression which has terms that are of a degree 2, and then the difficulty is somewhat reduced by the fact that you, instead of dealing with a polynomial expression of 2 terms, 2 variables, you now have a polynomial expression in 1 variable. So I would think that it would be a little bit easier to manipulate 1 variable as opposed to some polynomial expression that has 2 variables. All right, so how does this work? How do you subtract a polynomial expression from another polynomial expression? Well, we're going to need to add our apples with apples and bananas with bananas. And in this instance, because we have a subtraction symbol, we need to remember that subtraction is the same thing as multiplying by a -1. So what we're really doing here is we've got a polynomial expression, 8x squared plus 2x plus 7, and that is being multiplied by -1. On the other hand, you've got 5x squared plus 10x plus 25 on the outside set of parentheses. By distribution law, we should be able to multiply the -1 across each of these terms. Remember the distribution law, guys. We've talked about it in class. This is where we're going to need it. And we get -1 times 8x squared plus -1 times 2x plus a -1 times 7. And nothing is happening to our 5x squared or our 10x or our 25. So we'll just leave them there for now. Now, positive and negative is a negative. So you get -8x squared. Positive and negative is a negative. You get 1 times 2 is 2. So you get 2x. Positive and negative is a negative. 1 times 7 gives you 7. So at this point, you now have a polynomial expression, 5x squared plus 10x plus 25 minus 8x squared minus 2x minus 7. And all you have to do is remember the commutative law of arithmetic. We're going to line up our x squared terms with x squared terms. We've got 5x squared minus 8x squared. We have 10x. Subtracting 2x, we have 25 and a 7. And so what are we going to get at the end of the day? Well, let's see. By the addition of like terms principle, we can add x squares with x squares. 5 minus 8 should give me -3. So we'll write -3x squared. 10 minus 2x should give me a positive 8x. And then when I do 25 minus 7, that should give me, let's see, well, that would be 18. So this is my answer. When you're subtracting polynomial expressions, you need to really be very, very careful to keep track of the negative sign within your expression. Now, we were dealing with a polynomial expression where each of our terms was positive. So ultimately, when you perform subtraction, it wasn't, at least in principle, that much different from taking, say, 5x squared and subtracting off 8x squared from it, or 10x and subtracting 2x, or 25 and subtracting 7. And so a lot of students get into some very bad habits when they're subtracting polynomial expressions because it seems so straightforward, and it frankly is. But we have to remember the accounting. If we goof up on our accounting at this critical junction and we get into the habit of doing some very, very lazy mathematics, well, that's really what's going to separate the C students from the A students. It's going to be just being lazy with our math and not taking into account when we should be, say, adding and or subtracting negative terms properly or correctly. So just as an example of that, let's say we've got -8y squared plus 2y minus 10. And say we're subtracting from this expression 4y squared minus 21y plus 15. Okay. The first step for these polynomial expressions is that we need to make sure that all of our terms are outside of the set of parentheses. You'll note at this step 3 of the addition of the last two polynomial expressions together that when we actually were able to start adding terms was when we had all of our terms outside of the set of parentheses, and we then were able to do some rearrangement, right? Usually we'll be given a polynomial expression where both terms of both independent polynomials are inside of a sequence of parentheses. And this is to indicate to students that really this -8y squared plus 2y minus 10, this is a thing. This is a mathematical object and has its own unique properties. And we're subtracting from that mathematical object another mathematical object, this 4y squared minus 21y plus 15. And so because they're their own objects, we use the parentheses in order to indicate that you got two different things that are either adding or subtracting with one another, as is the case here. So the first step we have to do is utilize what is known as the associative law correctly. So we're going to use the associative law. We will remove the parentheses. We're going to get negative 8y squared plus 2y minus 10 for our first term. And unfortunately, for our second term, we can't just use the associative law, because what's happening when you're subtracting is that you're actually multiplying entire sequence of parentheses by a -1. So in this instance, we have to go through the rigmarole of multiplying a -1 by this entire expression here. So, and that's not too much problems, right? It's just that a lot of students are going to want to take shortcuts, and they'll wind up with a wrong answer when they're doing this. So my recommendation to students is, regardless of how much time it takes to write out a polynomial expression, always do it, because, unless you just like getting wrong answers, which there are some students that do, they have sloppy work, they're going to get wrong answers. Unless you just naturally like to get wrong answers, it's not but 5 seconds worth of work in order to ensure that you are in fact obtaining the correct calculations. And so what we arrive at is this new expression, -8y squared plus 2y minus 10 minus the quantity 4y squared plus 21 minus 15. Okay, so what can we do with that? We're going to, again, combine our like terms. We'll have the -8y squared minus 4y squared, positive 2y plus 21y minus 10 minus 15. 21 plus 2, that's going to give me 23y. -8 minus 4, well, if I owe you $8 and then I owe you 4 more, I should owe you in total $12. -10 minus 15, that's going to give me -25. And voila, we have a new polynomial expression, -12y squared plus 23y minus 25. And this is our answer. Naturally, we may extend this idea and make things a bit more complicated by having terms that are outside of our sequence of parentheses. So you might have, say, 5 times -3 p squared plus 2p minus 4 times 3 p squared minus 4p. And the only thing that we need to watch out for in this instance is that we need to make sure we're doing distribution correctly. When you have 5 times the quantity -3p squared plus p, this is not 5 times -3p squared plus p. That's not how this works, okay? It's 5 times the first quantity plus 5 times the second quantity. Okay? Believe me when I say this, I have students that are in the introduction, or I guess it would be the intermediate algebra course, who make this mistake, who can't do distribution correctly. So we have to be able to do distribution correctly, and when we're distributing, my recommendation would be to just wrap everything in parentheses, especially those negative numbers. And then when it comes to, say, distributing this 4, don't distribute the 4 and forget about the subtraction symbol. Because we've got the subtraction symbol, we have to be able to remember that when we're subtracting 4 sets of this quantity, it's the same thing as adding a -4 multiplied across the quantity itself. So you've got a -4 times the quantity 3p squared minus 4p. And by the distribution law, you'll multiply the -4 by 3p squared, and we'll have the -4 times -4p. So we got 5 times negative 3p squared and 5 times 2p. Okay. Negative negative is a positive. 4 times 4 is 16, so we get 16p. Positive negative is a negative. 4 times 3 is 12p squared. You get 5 times 2 is 10. And positive and negative is a negative. 5 times 3 is 15. So you get 15 squared plus 10p minus 12p squared plus 16p. And of course, we can do some rearrangement. So you get 15p squared minus 12p squared plus 10p plus 16p. When you start adding like terms, you should get negative 27p squared. And 10 plus 16, that should give us 26p. And this would be our answer. The long and the short of it is that polynomial expressions are pretty interesting because they appear to obey both the commutative and the associative law. Recall that for the commutative law, we just said that anytime you take two or more numbers, to be specific, almost 3, but it's actually 2 or more numbers, you may change the specific order of those terms when you're adding them together. Now, for polynomial expressions, when we're adding polynomial expressions, you know that it's not really going to matter which term you add in which order. For the associative law under addition, we said that when you add a quantity with the sum of 2 other quantities, that's the same as adding the initial basically taking a sum of the first 2 quantities and adding it with the third for any 3 numbers or for any 3 terms. And for polynomial expressions, it's exactly the same. When you have a polynomial added with the sum of 2 other polynomials, this is going to be the same thing as taking the first 2 polynomials and adding it with the third. It's just an interesting fact about polynomial expressions, and it starts to essentially indicate to us that there's perhaps a deeper structure in play when we're talking about polynomials or when we're talking about numerical systems in general, and which is in fact very, very interesting when you get right down to it. I should make a note about the notation of polynomials. When I have p parentheses x, this is the notation for an arbitrary polynomial. Let's recall the meaning of the word arbitrary. When I say arbitrary polynomial, it means that it doesn't matter what the polynomial actually looks like. So arbitrary just means doesn't matter what something looks like. So you could have a complicated polynomial. I could have a really, really simple polynomial that I'm dealing with. When I'm trying to express the idea that I can take these quantities and start adding them together in different ways, we'll use the notation p of x or q of x or s of x just as a shorthand way to indicate that we're dealing with polynomials in an algebraic sense, okay? In an analogous manner to A, B, and C, representing 3 individual quantities. This S of x, Q of x, and P of x represent individual polynomial expressions. And so individual polynomial expressions may be said to obey the commutative as well as the associative law of arithmetic. That's all I've got for you guys today. Take care.